And so we're going to take now just a very brief look at deep learning. And the reason we're not going to spend much time on deep learning in this module is because the manner in which neural networks or connectionist networks have been employed has changed as the field of our understanding of human cognition, human social practices have changed. In that time, the term artificial intelligence has changed its meaning beyond recognition. Where we started this course, we looked at the profound deliberations of people like Warren McCullough in trying to understand the link, the role between the brain and mathematical logic. And that gave rise to an idea grounded in a strongly rationalistic view of humans, that there was such a thing as intelligence which could be implemented mathematically. That dream has gone. That is no longer the case. And when the term artificial intelligence is used today, it's used usually, I would say always, inappropriately. But the field has produced very spectacular results, so we need to understand what they are and to clearly differentiate them, both from the philosophical beginnings of the field of connectionist network modeling, and from the second wave, where these models were used to address questions to do with human cognition within cognitive science. Deep learning is something else. Artificial intelligence is one term that's bandied around. Data mining is another one. And when you hear the term data mining, be cautious. Data do not exist. Data are created. Data are made by people in selecting some aspects and recording some aspects of reality. They are marks. They are scratches left behind by something. Data is not a natural resource out there. Ignoring where the data comes from is perhaps the greatest sin committed today in neural network mining and machine learning in general. In deep learning, we're using networks which are similar to the ones we have studied and will continue to study here. They tend to have very many layers, to involve numbers of parameters that are orders of magnitude larger than anything we will be looking at. This field has emerged out of the confluence of a variety of factors which we'll look at. And the kind of data sets that they're working with very often are not patterns like our little 3-number and 4-number patterns, but rather take a photograph. That photograph can be represented as a bunch of numbers. If you saw it as a bunch of numbers, you would not see it as a photograph. You would see the numerical values associated with each pixel. That is what the network works with. It works with numbers, not with images. But those numbers are derived very often from images. Likewise, numbers at the output can in various clever ways be interpreted by the human as mapping to letters and words and so on. So it can seem that the network has produced language, it has produced only numbers. Deep learning typically maps from a low-level input, by that I mean the raw numbers of a photograph, for example, to a high-level symbolic representation, for example, a label. The mapping has to go through many levels as features are recognized and recombined and so on, and the mapping can take many kinds. So a lot of these networks are quite heterogeneous. That is, they combine both supervised and unsupervised learning techniques. But they have been enormously successful in generating hype. And here you can see the font used for this particular article is probably the most noteworthy thing about the article. It's ghastly and it speaks of cheap science fiction, building the Google brain. It's worth noting that the subject of this article is Geoffrey Hinton. Geoff Hinton has been at the center of connectionist research in all 3 waves. He was one of the first people to work with neural networks. He was one of the people seminally involved in producing the PDP volumes in 1986, and he has since gone to work for Google. And he's a remarkably clear thinker. He's a formal thinker, and modeling is his forte. Nonetheless, this continuity of persons and technical terms should not obscure the fact that the field has moved on entirely, and its concerns now are entirely different. So a common approach is to start with a big data set, so maybe millions and millions of richly structured data, such as images. And frequently unsupervised learning techniques, such as the Hebbian learning technique we looked at, for example. A more common one is called a restricted Boltzmann machine. They're used to extract statistical features of this set. So to develop sensitivities to certain structural elements which recur. Having extracted some features, those themselves can be subject to a similar analysis, and we can induce low-level features and build up towards more high-level features. That's typically an unsupervised learning process in which statistical regularities of the dataset are made manifest. After that, then these feature maps, as they're now called, can be subjected to further processing by further networks. For example, networks to do classification, as we've just seen, or networks to re-represent the data in a very, very different way. The details of all this are unimportant to us. At the heart of this is nothing other than exactly the kind of processing we've been seeing so far. We may have very many layers. Here, for example, a great number of layers starting with images and extracting features. And when we do so, what we can ask of a hidden unit at some stage is, what are you sensitive to? What statistical features of the input are you responding to? These will be prototypes of recurring elements. So here, for example, after 1, 2, 3 layers of feature extraction, we have a hidden unit which is sensitive to the presence of a diagonal line within a restricted field of the image. Several processing steps later, we have a hidden unit which is responding sensitively to something which looks like a face. It knows nothing of faces. These are statistical patterns. There's another one that seems to be responding to cats. So here we can see a symbolic representation, a caricature of a very complicated learning system which starts with an input of an image and leads ultimately to an output of a label, a man sitting. So this seems to describe the image. The mechanics of this are actually inspired by old epistemological theories and by more modern representational approaches in cognitive science and neuroscience. So Hubel and Wiesel, whose work you may have met in my previous module on the Introduction to Cognitive Science, made very popular a view of visual processing in the brain by which one understands the brain to be doing something of this nature, that is, extracting low-level features and then gradually constructing an internal representation, which ultimately resembles, in some sense, the stimulus that gave rise to that. Now, there are lots of problems with that in neuroscience. This is not universally acknowledged, but it has been influential, and it has fueled this kind of approach because this seems, in some respects, to be mimicking this old epistemological idea. That motivation has become much more complicated within cognitive science, but it persists within deep learning. I would suggest to you that since the onset of deep learning and the demise of the original goals of the term artificial intelligence, what we're looking at when we look at deep learning, at connectionist modeling in this sphere, has far more to do with issues concerned with privacy, politics, control, authoritarianism, and capitalism than human cognition. For that reason, it goes beyond the bounds of this module, but we need to be concerned not only with how science is done, but how science is abused as well. So we're not going to try to follow the latest and greatest hits here, though we'll look at a few of them. But it is worth noting that even the latest of these networks all grew out of the same kind of humble beginnings that we have traced, And when we speak of a network doing something, what we're talking about is a process of doing sums, nothing else. Numbers in, numbers out. The interpretation of the numbers lies 100% with the humans. So there's the historical timeline that you hopefully revised there, with the green arrows represented 3 waves of neural networks research. And this third wave came about through a confluence of several things. First of all, data sets became available that were unimaginable. Even 10, 15 years ago, nobody could have imagined the size of the data sets that people are working with now. Working with these data sets means exploiting vast computational resources. Some of this was made possible through advances in computers that were originally made for video gamers. These are the graphics processing units which allow for very high definition images, and they are ideally suited to image processing. And a lot of the success of deep learning comes about from image processing. By no means all of it, but this is one reason that this field has advanced so far, is that there was a parallel technological development in video gaming that greatly facilitated the rapid processing, parallel processing of images. And when these two developments came along with generic advances in machine learning, we get deep learning networks which are capable of what appear to be extraordinary feats. And I want to show you a general architecture that has become very popular, which is responsible for very many of these greatest hits. And it is a somewhat troubling development. This is the Generative Adversarial Network. This is a generalized approach in which there are several networks involved. Supposing, for example, that we have a database of real images and they're all of the same size. Okay, we have a bunch of Polaroid photographs digitized so we can express them in numbers. Well, we can generate a fake one just by generating random numbers that have the same dimensionality. So if every Polaroid picture is represented by 2 million numbers, then we can just generate random strings of 2 million numbers. That's what the generator network does there. And then we can use a neural network to see, can it tell the difference between a real image and a random image. It's a discrimination task like we've seen before. And of course, at the start, this is trivially easy. But we can introduce an error function which improves the performance of the generator network so that it gradually generates random patterns which are more successful at challenging the discriminator network and ultimately at fooling the discriminator network. That is, we can allow this adversarial comparison of the real with the fake to feed back into the process of tuning the weights so that the ability of the generator network to generate fakes is vastly improved. This produces something of an arms race, and it's a real problem. It was introduced only in 2014, but it has come a long way since then. You've met a previous version of this arms race in the CAPTCHA. So the CAPTCHA was an attempt to stop automated systems making use of web services, which were intended to be used by people. For this purpose, a test was provided to the user, which it was assumed would be hard for machines to do and easy for humans to do. You've met these before, entering letters and numbers which are displayed with all kinds of distracting elements, jagged edges, distortions. What you will have noticed over the years is that these have got much harder because the algorithms for faking the human performance have likewise got better. So there's been a motivation, this is in the social domain now of computer programming, there's been a motivation to improve the algorithms that mimic human performance. And it's now got to the stage that the algorithms are probably as good as, if not better than, the humans at solving the captchas. And so the captchas are largely going away and other kinds of tests are being involved. You've probably found yourself trying to count traffic lights and bicycles in pictures, for example. So that's an example of a similar arms race. Well, this has been quite remarkable in the field of neural networks. So on the left-hand side here, you see the kind of training set that would have been used back in the 1990s for training in the field of machine vision, training networks to recognize handwritten digits. These were notoriously hard to recognize, and you're familiar with the difficulties of reading handwriting. A generalized adversarial network can learn to fake handwriting, and so all the images on the right-hand side are fake handwriting. They look indistinguishably wobbly and unpredictable from those on the left-hand side. But this is a very simple domain. Handwritten digits don't generate the same kind of surprise. If you care to visit this website, thispersondoesnotexist.com, it will generate for you an entirely novel image of a face of a person who doesn't exist. So it'll generate a fake which has been trained on using a generalized adversarial network trained from real faces, so that the generated face appears to the discriminating network to be plausibly of a face. And you get things like this. This is not a person. This is a fake generated by a neural network. This is not a person. You can see where we're going with this. Images have attracted the limelight here. Most of the work has been done on images, and there are real reasons for that, among others because of the processing power of graphic processing units developed for video gamers. More recently, there's been a lot of work in text generation. Now, we will approach the relationship between numbers and language in a very primitive fashion in this module, but it is possible to develop numerical codes for language, and in this way we can get networks to generate numbers that can be interpreted as language. A generalized adversarial network for producing convincing text has developed spectacular results. The system in question is called GPT. These are trained on enormous text databases. Of course, we have almost unlimited amounts of text, and they're taught to produce novel text output based on what they saw recently. So GPT-2 was released about 4 years ago, I think, and it was, at that time, wildly impressive. I've given an example there where I provided a seed. I said, I see this class would like to learn about deep learning. Let me tell you. And then I let the machine or the network carry on, and the output is shown there, and it's rambling. It's not psychologically plausible, but it's linguistically plausible. And this was considered to be troubling. The language generated here still makes no sense, but it's getting very, very close to language that does make sense. The successor to GPT-2, GPT-3, emerged 2 years ago, and they attempted to keep it secret, and it has since escaped. The potential consequences of this are absolutely awful. In a world in which misinformation and disinformation campaigns are the chosen method of warfare, in which the generation of text can be done automatically and that then piped into social media networks by bots, you have the potential here for something which is profoundly destabilizing for society. If people can no longer tell whether written words were written by a person or by a machine, and those machines can be trained to do almost whatever you like, the consequences are dire. One of the required readings for this week is a sample article, quote unquote, written by GPT-3. And when you're reading it, bear in mind that the network takes numbers and produces numbers. It knows nothing of language. And in fact, we have a linguistic problem in talking about these networks. I've always been at pains here to stress what lies in the domain of interpretation of the researcher and what we should properly attribute to the network. To the network, we should attribute doing sums. But these days, if you go on YouTube, you may see videos like these. An AI makes a video game after watching tennis matches. Stickman AI learns to walk. This artificial intelligence tried to crack the Voynich manuscript, and this is what it found, and so on. Furthermore, when you watch a video of this, you'll see a stickman, for example, appearing to learn to walk. The network has learned nothing about walking. Networks know nothing about walking. Rather, numbers have been used which can generate animations which the viewer sees as walking. This kind of failure to distinguish between what the network is doing And what the domain is that we're interested in, walking or tennis, is troubling. The Voynich manuscript is a case in point. This is a manuscript that doesn't look like the illustration there. It is a genuinely perplexing manuscript from around the 1500s, which has never yet been deciphered. Among other things, deep learning tools have been thrown at it to see what patterns obtain, and those kinds of results have been discussed ad nauseum in the technical literature, and they are distressing because they try to circumvent expert knowledge, try to circumvent real understanding of a domain. So networks don't steal bananas, networks don't learn to walk or to survive or to interpret text. Networks do nothing but sums, and this short look at deep learning should give you hopefully some of the required caution as we enter into a profound new age of machine learning.